So what we're going to do here is we're going to compare the radius of ions, okay, in comparison to their parent atoms. Okay, so for example, right, if I said, let's say I had a sodium atom, right, versus a sodium ion, right. So here, if we were to compare sodium ion versus sodium atom, okay, we'd realize that when we talk about the radius, right, when we talk about the radius, sodium ions are actually smaller than sodium atoms. And the same thing applies to magnesium ions versus magnesium atoms. Okay, and the same thing for aluminum ions, for example, versus aluminum atoms, right? The idea here is that cations, okay, have a smaller radius, okay, have a smaller radius or have a smaller size, okay, are smaller in size than the parent atom. Okay, than the parent atoms. All right, so again, the reason why is because when we're usually forming cations, first of all, right, what happens is that the valence electrons are lost, right? The valence electrons are lost when cations are formed in most cases, right? In these three examples, right, we know that the valence electrons are lost, which means that the number of shells, right, decreases, right? So we can say that the cations have fewer shells, right? Now, what this means is that the first of all the ratio of protons to electrons, okay, increases, right? Again, that's the same as saying the nuclear charge per electron. The nuclear charge per electron increases. Okay, the nuclear charge per electron increases, and obviously shielding decreases, right? Because you have fewer shells, right? So for example, if you look at a sodium atom, right, the outer electron is in the third shell. It was being shielded by two inner shells. And a sodium ion, the outer electron is now in a second shell, right? It has the same configuration as neon. So it's only being shielded by one inner shell. So obviously, if the cations have fewer shells and you have a greater nuclear charge per electron, right, and you have lesser shielding, what that means is that nuclear attraction of outer electrons increases, right, and we can say that, right, we can say that the outer electrons are held closer to the nucleus. Now, if we compare the relative size of anions with their parent atoms, right? So, for example, if you were looking at something like a phosphide ion versus a phosphorus atom, right? The anions are larger than their parent atoms. Okay. So similarly, sulfide ions are larger than sulfur atoms, right? Chloride ions are larger than chlorine atoms. So we can say that anions are larger in size, okay, or have a greater radius than their parent atoms. Now to understand this, right, we're going to look at the configuration of these atoms and the ions. Okay, so for example, if you look at a phosphorus atom, right, the configuration is 1s2, 2s2, 2p6, 3s2, 3p3, right? Whereas a phosphide ion, right, the p3 minus, right, that phosphide ion, it has 3 extra electrons, right? So its configuration is 3p6, right? Same configuration as argon, right? Now, if you just look at the outermost subshell, okay, or the highest energy subshell, which is the 3p subshell, right? You look at the configuration, you know that here all the electrons are unpaired, right? All the electrons are unpaired. Whereas in the ion, what you have is the electrons start pairing up, right? The electrons start pairing up. So the atom is 3p3, whereas the ion is 3p6, right? So you have paired electrons. So what that means is that because of the pairing of electrons in the anion versus the parent atom, you have more pairs of electrons, so you have greater spin pair repulsion. So the electrons are repelling each other. The electrons, if you think about the electrons, right, in the outer shell, because they're now starting pairing up, there's actually an increase in the repulsion between the electrons. There's actually an increase in the repulsion between the electrons, so they want to spread further apart, which means that the radius of the phosphide ion, because of the increase in spin pair repulsion, because these electrons are repelling each other more in the outer shell, they want to spread further apart, right? Because of that increase in repulsion, right, we have a larger radius for the anion. So we can say over here that anions are larger than the parent atoms because, first of all, the ratio of protons to electrons, right, decreases. Okay, again, you can say nuclear charge per electron decreases. The nuclear charge per electron decreases, right? And the second thing that happens here is because, right, in the anion, right, there's, right, electrons go from being unpaired, to paired electrons, right? Hence there is an increase in spin pair repulsion. So here again, in the phosphorus atom, right, we had 3 unpaired electrons, where in the phosphide ion we had 3 pairs of electrons. So each of those unpaired electrons was paired up, right? Now, if you contrast that with, let's say, something like a sulfur atom versus the sulfide ion, right? The sulfur atom has a configuration of 3p4, whereas the sulfide ion has a configuration of 3p6, right? So what we see is that for a sulfur atom, we just have one pair of electrons, right? Only one of the orbitals has a spin pair, right? And then the sulfide ion, again, what we have is we have now pairs of electrons, right? So what we're doing is, because we're pairing up these electrons, right? Because the anions have more pairs of electrons, you have greater spin pair repulsion. Greater spin pair repulsion means that the electrons want to space themselves apart, which means that the anions would be larger than the parent atoms. And you see the same thing for chloride as well. You see the exact same thing for chloride as well. Okay. In chloride you have the chlorine atom has a configuration of 3p5, right? Whereas the chloride ion again ends with 3p6, right? So chlorine atom, right, has this configuration here, right? The chlorine atom just has 2 pairs of electrons, and one of the electrons is unpaired, and that one unpaired electron, right, when you form the anion, that one unpaired electron then ends up being paired. So in all cases, what you're doing is you're increasing the number of spin pairs, right? You're always whenever you're forming an anion from a parent atom, you are increasing the number of pairs of electrons, right? Or number of paired electrons. Hence you have greater spin pair repulsion, and hence the anions have a greater radius than the parent atom. So now if we summarize the trends that we've seen for atomic and ionic radii, right, what we see is the following, right? So here, let's look at period 3, for example, right? If we look at period 3, right, looking at period 3, and we have the radius on the y-axis, and we have atomic number on the x-axis, right? And we've already learned that the atomic radius obviously decreases across the period, right? Because the nuclear charge increases, the number of shells remains the same. So the outer electrons are attracted more strongly and held closer to the nucleus, right? So we see this trend in the atomic radius. We see this consistently decreasing trend in the atomic radius, right? So here we have sodium, here we have magnesium, aluminum, silicon, right? Phosphorus, we have sulfur, and then we have chlorine. Right, so we see this consistently decreasing trend. But now what we also see here is that the cations are smaller than the parent atom. So if you look at sodium cations, right, magnesium cations and aluminum cations, for example, right, they would be smaller than the parent atoms. So this is the trend you would see for the cations, right? They would be smaller than the parent atoms, right? And similarly, obviously, if you were looking at silicon, silicon can make for silicon, as far as the trend is concerned, you can have cations or anions, okay, but the idea is the same, right? You have Al3 plus, and then if, for example, if you had something like, I'll show silicon like this, right? You have Si4 plus, right? And then what you see is that the anions are much larger than the parent atoms, right? All of these guys have the configuration of neon, right? They've lost their valence electrons, these atoms, to form the cation. Whereas if we talk about the anions, right, in this case, all the anions will have the configuration of argon, right? So if you look at the Si4 minus ion, right, that will be much larger than the parent atom. If you look at the phosphide ion, it will be larger than the parent atom. The sulfide ion will be larger than the parent atom, and the chloride ion will also be larger than the parent atom, right? So you see this trend here. Right? So you have Si4 minus, P3 minus, S2 minus, and then Cl minus. Okay, so this is the trend. This is the trend that you have for the ionic radius across the period. You see the zigzag trend, right? The cations are smaller than the parent atoms, and the anions are larger than the parent atoms. You just look at the ionic radius, right? What you see is that you see a decreasing trend for these ions. You see a decreasing trend for these ions, right? The radius for the cations, but then you see a big jump from the cations to the anions, and then again you see this decreasing trend. So the trend line in yellow shows the ionic radius, right? And the trend line in white shows the atomic radius. Now over here again, the question is that why do we see this decreasing trend, right? If you look at the cations, right, we see that when you look at the successive cations in the period, the ionic radius is decreasing. Right? You see the big jump to the anions, but then again you see this decreasing trend. You see this decreasing trend, right? And what we can say here is if you look at the cations, for example, right, we have sodium, magnesium, aluminum, right? They all have the configuration of neon, right? They all have the configuration of neon, okay? Whereas phosphide, sulfide, and chloride, they all have the configuration of argon, right? So sodium, magnesium, and aluminum are what we call isoelectronic species, okay? They're isoelectronic species. Similarly, phosphide, sulfide, and chloride are also known as isoelectronic species. So we talk about isoelectronic species, right? Okay. Isoelectronic species, right? Isoelectronic here means the same number of electrons. Same number of electrons. And let's look at some isoelectronic species here and compare their radii. So for example, here I have the oxide ion, fluoride ions, we have neon, we have sodium ions, we have magnesium ions. Okay, so all five of these species are isoelectronic, right? They all have how many electrons in this case? 10 electrons, right? They all have 10 electrons, right? So they all have 10 electrons in this example, right? And they all have the configuration of neon, right? Which is 1s2, 2s2, and then 2p6, right? And the question is, what is the trend in their radius? What trend would you see in their radius, right? So if I want to compare the radii for each of these species, right? Which of these species would be the largest and which of them would be the smallest? If you think about the radius of these species here, we know that the oxide ion would be the largest, right? And the magnesium ion would be the smallest. They all have the same configuration, right? So here shielding, repulsion between electrons, all of that is the same, right? The only factor that's affecting the radius is the nuclear charge, right? The only factor that's affecting the radius is the nuclear charge. That is the number of protons in the nucleus, right? And we know that here oxygen, right? The oxide ions have a charge of, the oxide ions have a nuclear charge of 8 plus, right? There's 8 protons in the nucleus. For fluoride, you have 9 protons. For neon, you have 10 protons in the nucleus. For sodium, you have 11. And then magnesium, you have 12. Right? Now, since they all have the same electronic configuration, the greater the nuclear charge, the more strongly the outer electrons will be held, or more closely they'll be held to the nucleus, the smaller the radius, right? Because here again, the configuration, shielding, repulsion, they're all the same. They have the exact same number of electrons, same repulsion, same configuration, right? So the only factor that's affecting the radius is the nuclear charge. Greater nuclear charge, smaller radius, right? So if we talk about this trend, we know that the oxide ion will be the largest, right? And the magnesium ion here would be the smallest, right? So when we talk about isoelectronic species, okay, when we talk about isoelectronic species, right, the greater the nuclear charge or the number of protons in the nucleus, right, again, nuclear charge is the number of protons, right, the smaller the radius. The outer electrons are more strongly attracted to the nucleus, right, because you have a greater nuclear charge, more strongly attracted to the nucleus, and hence they are held more closely by the nucleus, right? And held closer to the nucleus. So again, the outer electrons experience greater, you can also say the outer electrons experience greater nuclear attraction, right? They experience greater nuclear attraction and therefore are held closer to the nucleus. Okay, so that's the idea here. So what we saw in this trend, right, for the atoms versus the ions, right, we saw this, that sodium, magnesium, and aluminum, right, these were all isoelectronic. So the species with the greater nuclear charge would have a smaller radius, right? All of these guys had 10 electrons. Similarly, these species were all isoelectronic. They all had 18 electrons, right? The same configuration as argon. The one with the greater nuclear charge will have the smaller radius, okay? So whenever you have isoelectronic species, the nuclear charge is the only factor that affects the radius.